I can't remember what I've done in the past for the review. If I have a specific exam review, or I just say it's basically what's been on previous tests plus two other things. So I'll let you know. So it's going to be what's on the previous tests, and also there'll be a L'Hopital's rule problem, and there'll be a improper integral, meaning where you integrate to infinity. And then some things I'll specifically, depending how far we get in chapter 10. But I've got to check whether I've done a exam review or not for calculus. Since a lot of it builds on previous stuff, it's not that. And the fact that I'm going to pick out certain topics from previous tests that just make it different, just kind of a review. So I don't have an answer for you yet. I'll have to look at my YouTube channel and see what I had last time. If I do put out a review, it'll be on Monday. Most of you are not going to be studying this weekend, as far as I can tell, since it's prom. So I made it through most of the tests yesterday. I've just got to go, and I'm hoping to finish today. So we were talking about the calculus of parametric equations, and we were looking at this particular case right at the end of class. So let's just review where we were. So if you have parametric equations for x and y, you take the derivative of the y parametric equation with respect to t, and you take the derivative of the x parametric equation with respect to t, and that ratio will give you dy dx, which is the slope of the tangent line. So if you take dy dt, where y is 3t minus 1, you just get 3. And if you take the derivative of t square root of t, which is t to the 1/2, you'll get t 1/2 t to the minus 1/2, which is 1 over 2 times the square root of t. So the dy dx is just going to be dy dt divided by dx dt. And if you do that, you get that. And also notice, if I wanted to find dy dx in terms of x, I can go back to my original parametric equation, one of my parametric equations, x equals the square root of t. So I'll get dy dx is equal to 6x. So I'm taking this and I'm substituting in for that. So let's prove that's true by, we're going to eliminate the parameter from the original expression and make it dy y is a function of x instead of x a function of t and y is a function of t. So we'll say eliminate the parameter from these two equations, the same two equations. So if we want to solve for t, we're going to solve for t using this equation. So we'll square both sides. So you get x squared is equal to t, and we'll substitute that into here. So we get y is equal to 3x squared minus 1. And then if we take the derivative, dy dx, find the slope of the tangent line, when it's in this explicit form, you'll get 6x, which is exactly what we got doing it as a parametric equation. I mean, in this case, there wasn't much, there's not a whole lot of point in writing the equations in parametric form, because you can write them in y versus x. But a lot of times there are cases where you have curves that you can't define as y as a function of x, but you can define it in a parametric form, and then you can find the slopes of the tangent lines for those interesting special curves. So let's look at another example. So this is a circle with a radius of 2 with the center at 0. And the parametric forms of the equations for a circle are just x is equal to r cosine theta or cosine t, and y is equal to 2 sine t. So we're going to find the slope of the tangent line here, and we have a pretty good idea of what the tangent line is going to be, what the answer should be, because if we just draw this curve, or this, if I draw it like it's just a circle, radius 2. So when t equals 0, you're right here. When t equals pi over 2, we're here. When t equals pi, we're at that point. And if t is equal to 3 pi over 2, we're there. So the slope of the tangent line should be undefined at t equals 0. It should be 1 at pi over 2. It should be undefined at pi. Should be 0. Pardon me. Should be 0 at these 2 points. The slope. And if we take if we look at t equals pi over 4, the slope of the tangent line should be negative 1. And at 3 pi over 4, it should be positive 1. At 5 pi over 4, it should be negative 1. And at, what's the next one? 7 pi over 4, it should be positive 1, the slopes of the tangent line. So let's see if that happens or not. So we said that dy dx, the slope of the tangent line, is dy dt divided by dx dt. So what we do is we take the derivative with respect to y, with respect to t, sorry. So the top part. So we're going to take the derivative with respect to t of y, which is 2 sine t, and we divide that by the derivative with respect to t of 2x is cosine t. Okay, so that's the dy dx. So let's add a page, and so the derivative of this with respect to t is going to be 2 cosine t, and the derivative of this with respect to t is negative 2 sine t. So that's dy dx. So that's negative the cotangent of t. Cosine over sine is cotangent. So let's just make a table up of cosine of t versus t, and we'll pick. How big kind of table can I make? Let's see what happens here. So this is t. This is negative the cotangent of t. So we're going to do 0, pi over 4, pi over 2, 3 pi over 4, pi, 3 pi over 2, and I'm skipping 1 because I didn't have enough spaces here, 7 pi over 4. And of course the cotangent is 1 over the is going to be 1 over the tangent. And the reason I did that is we can use our calculator if we want to. So let's pull out our calculator. We could use the unit circle, but I'm going to just use my calculator instead. See what I get. Okay, so I'm going to put it in radians, which it is. And so it's going to be negative 1 divided by the tangent of 0. And I get divide by 0. So that's undefined. So what I'm doing is instead of because my calculator will do tangent but not cotangent. It's going to be negative 1 over the tangent of t. So here I get undefined. Okay, let's try the next one. So we'll put in pi divided by 4, and I get -1. And I put in pi over 2, and I get something wrong there. What was that? Why didn't it like that? Oh, yeah, it's 0. Calculator didn't like it because I asked for the tangent of pi over 2, which is undefined. But 1 over infinity is 0. Okay, and then if I put in 3 times pi over 4, so it's -1 over the tangent of 3 pi over 4, I get 1. And here I'll get undefined. Here I will get 0. And let me put 7 pi over 4 in. 1. Okay. So those are the values that I get using the parametric way of calculating the slope of the tangent line, which all makes sense. I mean, you've got undefined at 0, pi over 2 you got 0, pi you've got undefined, 7 pi over 4 you've got, or 3 pi over 2 you got 0, at pi over 4 you got -1, at 3 pi over 4 you've got +1, and at 7 pi over 4 you've got +1. So it all makes sense. In this case, there is some advantage because the original function here is an implicit equation. So we're not solving for x or y. If we have to solve for y, we actually have two functions. And if I had to take the derivative of that, I'd have to use the chain rule, and it wouldn't be. It's actually probably easier to do it this way than it is to do it that way. Okay. Now, back in Chapter 7, Section 4, which we kind of went over quickly, and we used the online integrator a lot of times because the integrals tend to be somewhat difficult. We might have a better chance of making it work now that we've had Chapter 8. But so what we saw was that the length of a curve is equal to the integral from x1 to x2, those are the x coordinates of the 2 points, times the square root of 1 plus dy dx squared times dx. Or, if you want to do it in terms of y, you take the integral from the y coordinates of the 2 points, and you integrate the square root of 1 plus dx dy, so it's the derivative in the other direction. So that was the rectangular coordinate version of finding the length of a line. The parametric form looks like this. So you integrate from t at the beginning to t at the end, and you take the square root of the derivative of your, so f of t is your x coordinate. So this is the parametric equation for x in terms of t, and g of t is the y coordinate of the path as a function of t. So in our previous case, f of t would be 2 times the cosine of t, and y would be equal to 2 times the sine of t. And you take the derivative with respect to time, and you square them, and you take the square root, integrate with respect to t from the two values of the parameter. So actually, let's do it. Let's do what we just did. So here we've got a circle, radius 2. The parametric equations for a circle of radius 2 were, as I just said. So let me add a page. Let me redo this. So we're going to have some coordinate system here. We already know the answer, but let's show you how you do it doing calculus instead of just memorizing the answer. So what we have is we have this circle, and it has a radius of 2. r equals 2. The x parametric equation was 2 cosine t. The y parametric equation was 2 sine t. So if we take the derivative dx dt, let's pull this down again. Here's the equation. This is going to be dx dt. So that's dx dt is what we, according to the terminology, is f prime of t. This is f of t, and this is g of t. So we're going to take the derivative with respect to t, and that's going to be equal to derivative of the cosine is negative the sine, so we get negative 2 sine t. And dy dt, which is also g prime of t, is going to be 2 cosine t. So if we plug those in to calculate the surface, or the distance along this line, which we know is 2 pi r, it's the circumference of a circle, we would integrate from 0 to 2 pi. That's how the parameter has to vary to go from here. Here's t equals 0, and it goes around t equals pi, t equals 2 pi. So that makes a full trip around there. So we integrate from t equals 0 to t equals 2 pi, and we take the square root of f prime of t, which is this thing. So it's negative 2 sine t squared plus g prime of t, which is 2 cosine t squared, and we multiply by dt. So let's see what happens. So we got integral from 0 to 2 pi of, so we'll get 4 sine squared t plus 4 cosine squared t dt. We can use the Pythagorean identity. So what we know is that sine squared t plus cosine squared t equals 1. So what we'll do is we can factor out the 4. So we'll have 4 times sine squared t plus cosine squared t, and that becomes 1. So we get 4 square root of 4 square root of 4 times 1. And the square root of 4 is 2. And the integral of 2 dt is just 2t. So we get 2t evaluated between 0 and 2 pi, which is going to be 2 times 2 pi minus 0, which is 4 pi, which is equal to 2 pi times the radius. So if we had done this, if I had done it for a, instead of specifically for a circle of radius 2, if I just put r in there and r is constant, I'd end up with the answer being 2 pi r, which is the circumference of a circle. So that's kind of how you do the calculus version of this. Now if we had done it using the rectangular form, that would have been a lot harder as far as coming up with the solution. But by writing the curve in the parametric form, it ends up that problem's easier. So let's try another one. Actually, let's see what the heck this thing looks like. So it's t is t squared plus 1, y is 4t cubed plus 3, and we're finding the arc length from t equals negative 1 to 0. So I don't know what that looks like. So let's open up my two-dimensional graphing program. It's a parametric equation, and the parameters are t squared plus 1. Notice they use f of t and g of t in this graphing program, which kind of goes along with what we're doing here. We got y equals 4t cubed plus 3. 4 times t cubed plus 3, and we're going between -1 and 0. And let's zoom out. Zoom out is page down. Okay. So that's what we're looking for. It kind of looks like I don't know what it looks like. You know, it's hard to tell just because we're only looking at a small part of the curve. So who knows what the rest of it looks like. And you can kind of guess. What do you think? What do you think a guess would be for the length of the line? Somewhere between what? 3 and 4, right? Because if you look at the y coordinate, you go from -1 to somewhere between 2 and 3. So if you went to 3, that'd be 4 if it was a vertical line. So it's probably going to be around 4 units long, just as a ballpark. So why don't you guys see if you can at least formulate this thing. So this would be f of t, and this is going to be g of t. And let's bring the equation down that I just used. Where is it? Must have been this one. Maybe not. Where the heck was it? This one? Yeah, there we go. So what I'm going to do is okay, and we'll, just in case you didn't take good notes. So go ahead and set up the integral and look at it and see if you can figure out how to solve it. So you just got to take the derivative of each one of those with respect to t, square it, add them together, add the two terms together, look at it and see if it's something that we know how to do. It should be, because otherwise I wouldn't have put it in there. I wasn't expecting it to be raining today, this morning. It needs to stop raining. Yeah, it should be stopping soon. We're driving to Richmond this afternoon, so it looks pretty good. I've got a funny video to show you too. After we finish this, we'll look at the video. Well, I thought it was funny because it's my grandson, but to you, maybe you won't find it funny, but I'll humor me. So you get to this point, and then you got to look at what are we going to do. Anybody have any thoughts about how we might? We can't integrate that. Anybody have any thoughts? So let me give you a hint. So if you're trying to come up with kind of a U substitution, you would normally let the entire argument be U. But if you take the derivative, you're going to have 8t plus 500 and something t cubed, and there's nothing there. Evan, what do you think? Yeah, yeah, good. So, yeah, you factor out a 4t squared, which when it comes out of the integral, it becomes just 2t. So you'll have, yeah, need to read some space there. Oh no, I don't need to leave space because it's inside the integral. Okay, so it's going to be from negative 1 to 0 of 2t times the square root of 1 plus 144 divided by 4 is something. 36 plus 36t squared dt. Okay, so now if you let u equal 1 plus 36t squared, du will equal 72t dt, or t dt equals du divided by 72. And since we're doing a definite integral, we probably could go ahead and redefine it. So remember, when t equals negative 1, u equals, well, it'll be equal to 1 plus 36 times negative 1 squared, which is 37. And when t equals 0, u equals 1. So then what you can do now is, so the integral becomes the integral from 37 to 1 of 2 times the square root of u times du divided by 72. So TDT is du divided by 72. This is the square root of u. The 2 stays there. So go ahead and integrate that for me. And hopefully you can get an answer around 4. And again, you don't have to substitute u back in because we've redefined the limits in terms of u. Something doesn't seem right. Did I make a mistake somewhere? You're asking me why do you think why am I worrying about it? Because it seems like the square root of u is always above the x-axis, but we're integrating the wrong direction. So I'm going to get a negative answer. So while you're integrating it, I'm going to figure out why that, if I made a mistake or not. Maybe I didn't, but it seems like something's not quite right. 2t, 12t squared. 2t squared, 4t. I don't see anything. Let's see what happens. So we'll see what kind of number we get first, and then we'll worry about the why I think something's wrong. I remember this now. I remember this problem. Okay. So you get the number is pretty close, right? It's around 4. It's just a negative sign. And so, what's going on here? Because I don't think I made any. Well, I have made a mistake, but it's not one that is immediately obvious. And I think it comes down to when you factor out the 2t, it can be plus or minus 2t. So the reality is that, so it's kind of like when you take the square root of a number, it's plus or minus the square root. So when you factor this 2t out, it could be either plus or minus for the same reason. And actually, I did, when I was looking at this, I saw that. I saw, why did that have plus or minus? And yeah, notice this is from last year. And I had this plus or minus. I noticed that. And I thought, oh, where did that come from? I don't remember writing down plus or minus. Whoops. I don't remember writing down plus or minus. And that was because that was from last year or the previous year. So I'll probably forget it next year as well. So yeah, when you pull that out, it can be either plus or minus. And it turns out it has to be, negative is the right answer to give you a positive arc length. You can't have a negative length. Well, I guess you could if you switch the limits. Anyway, so it works. Okay, now we're going to watch the video. I'll stop my recording here. So we also had areas of revolution, and so the rectangular form was we took the radius as a function of x, which was usually just the y coordinate, which is the function, and then you multiply by the square root of 1 plus f prime of x squared dx. So you have that extra term here. So depending upon whether you're rotating around the x-axis or the y-axis, you have a different equation. You're again integrating between two values of t to define the curve. And so you take g of t here, which is the y coordinate. Y is a function of t. You multiply by dx dt, which is the derivative of f prime of t. This is g prime of t. Whereas if you rotate around the y-axis, you use the you're looking for the x coordinate as a function of time. So you use f of t instead of g of t. But the stuff inside stays the same. Okay, so there's your homework for section 3. So what is today? So these are all due at the exam. Okay, anything I assign after today, you can turn in at the exam. I'm still not sure what he was trying to ask, the question he was asking about. I thought the funny part, this is very nice. What did she say? He liked the milk. He thought it was very good milk. Okay. So we're going to go to section 4. So section 4 is dealing with a different coordinate system. And if you take Calc 3, one of the things that they'll look into is different coordinate systems such as the polar coordinate system, the cylindrical coordinate system, and the spherical coordinate system. So in this chapter, we just look at a two-dimensional case, which is the polar coordinate system. So we're used to using x and y to define a point in two-dimensional space. So I've got this point 6 comma 7, so that means we go 6 units in the x direction and then go up 7 units in the y direction. But you can also define a point in space by specifying its distance from the origin, which we're going to call r, and the angle of that line with respect to the positive x-axis. So the usual theta that we're used to. And because we love right triangles, as you physics guys know, what we can do is we can find the hypotenuse of this right triangle by squaring this and adding to this squared, and that'll be equal to that squared. So it's easy to convert from rectangular to polar coordinates relative to the radius. You just take the x-coordinate squared plus the y-coordinate squared, take the square root. The angle, which is in radians, is determined by the arctangent, but so you can take the ratio of the opposite side to the adjacent side. The problem there is, of course, that the arctangent is limited in its domain. It only goes from negative pi over 2 to positive pi over 2. So you've got to think a little bit. You've got to know that if these are both positive, then it's going to be in the first coordinate. If x is negative and y is positive, it's in the second coordinate. And if they're both negative, it's in the third coordinate. And if x is positive and y is negative, it's in the fourth coordinate. So you can use the arctangent to find basically the reference angle. We talked about that previously. And then once you have the reference angle and you can determine the quadrant from which ones what signs these are, then you can find the actual angle. So we're going to, instead of having a coordinate pair x, y, we're now going to have a coordinate pair r theta. The disadvantage of r theta is that you can go theta of pi over 4 is going to be equal to the same angle as pi over 4 plus 2 pi. There's always these multiples. So you can have more than one r theta value to give you the same point in space. So if you go just to here, that would be pi over 4. But if I went all the way around and came back to there, do you guys remember what the name of that kind of angle is from pre-calculus? If you have the same point, it's pointing in the same direction, but it's because of multiples of 2 pi. Pardon me? Reference angle? Yeah, no, that's just the reference angle is the angle between the nearest x-axis, positive or negative. Let me see if I can give you a hint here. Starts with a C. Something angle. Coterminal. Remember that? So yeah, a coterminal angle. So pi over 4 and 2 pi plus pi over 4 would be coterminal angles, because unless you knew that it went around another full turn, you would never know that they're actually different than each other. Okay, so we'll stop there. We will continue on Monday.